video is going to be a review of the SJL Instruments GigaWave 6400. This is a new sampling oscilloscope that they just came out with. I want to explain something before we get into the review. I've been working on this video for a little over a month. During this time, the software that the manufacturer has supplied has changed quite a bit. So as you're going through this video, what you're going to find is the menu structure has changed quite a bit from version to version. So as you're looking at the software, it may not have the same look or run at all like the way it's being presented during the review. My advice to you, if you're interested in this product, is go to their website and you can download the latest software. They have a demonstration mode that allow you to actually exercise it without buying the hardware. You can also download the manuals for it. That'll give you a lot better idea for how the software drives as well as what features are available. Also during this review you're going to find some things that are out of order, or I've actually reshot sections of the video. Again, that's just the nature of looking at a product that is just so new on the market. Alright, so on with the review. Hello again and welcome. At the beginning of the year, a member up on EEVBLOG that goes by the name of SJL Instruments posted about a new product that they were releasing. They have 3 different sampling oscilloscopes that they're introducing. There's a 2, a 4, and an 8 channel version. They all have an analog bandwidth of 6 gigahertz. So I've been having an ongoing dialogue with them, and they asked if I'd like to review one of these. So they've graciously provided this one to me. I haven't looked at it yet. So let's just go ahead and open this thing up and we'll take a look at it. I have no idea what this looks like. You go to their website, they don't actually have any photos of it. It's got some heft to it. So this is the GigaWave 6400. It has 12 bits of vertical resolution, 1 terasample per second equivalent time sampling. For comparison, my LaCroix 64XI has a sample rate of 10 gigasamples per second, and my WaveMaster can do 20 gigasamples per second. Of course, if you run those in wrist mode, you have a much higher sample rate. So that's what we're talking about here. This is a sampling oscilloscope. Designed and assembled in the USA. You can see it's RoHS compliant, and this is a link to their website. On the side we can see 6 gigahertz digital sampling oscilloscope. On the back they're showing a 4-channel version. I don't know if that's what's in the box, but I do know that there's a difference between these channels. They're not all the same. So channel 1 is always the trigger input. Another important note, you can see the inputs are rated for plus or minus 950 millivolts max. And before we open this up, we'll go ahead and put a wrist strap on. Alright, let's have a look at this thing. Oh, they did send the 4-channel version. Okay, so my first impression of this is, wow, this is actually all metal. Like, this is going nowhere. I don't see any plastic parts in this case whatsoever. You can see it has 6 Torx screws that hold the 2 case halves together. They provide you with a small Torx wrench, so it's almost as if they're expecting that you are going to take this apart. Yeah, that's the wrench for it. And they also supply you with a cable. Of course, this product requires that you have a PC to interface with it. I know that they support Linux as well as Windows. I'll be performing all my tests with this using Windows. The obvious advantage to a scope like this is it's very small. Fits basically in the palm of my hand. The next thing is going to be the cost. The 2-channel version of this sells for $22.95. This 4-channel one sells for $24.95. And then again they have an 8-channel version which sells for $28.95. Now I downloaded the software and played around with it a little bit before I received this. And another reason that you may want to consider this, that software is very simple to use. Of course, that's also kind of a downside because the software is fairly new. It's missing a lot of features. But to be fair, I've offered up some suggestions as far as what they can do to improve that software, and they've already made a release which includes some of that, and I know that they're planning to release another version next week, so they appear to be very responsive. Let's just have a look at the connectors that they're using. And you can see it's using a standard SMA. I had asked the manufacturer how many mate cycles these are rated for. They told me that these connectors are made by Amphenol. They're part number 901 10512-1. They're rated for 500 mating cycles, so you can take your connectors on and off 500 times, and they're also rated for 26.5 gigahertz. So the first thing I'd like to measure is how good is the port match of these different inputs. So we're going to start with the trigger input. You can see I have this attached to my Agilent P&A. This is a model E8357A. This particular one has the license enabled to allow it to operate up to 9 gigahertz. Again, you can see I just have port 1 connected to channel 1 of the oscilloscope. Another thing I'd like to mention is this is the cable that I'm using. This is a USB 2.0 cable, and this one happens to be 8 feet long. Now if you look at the manual for the oscilloscope, they talk about it requiring USB 3.0. From my conversations with them, apparently it doesn't require the USB 3.0 protocol. It just requires it for the higher current draw. So it's going to be fine running this with the USB 2.0 as long as it's plugged into a 3.0 port. Another thing that they mentioned is it's okay to run this thing off of a powered hub. Another advantage to this product is the manufacturer provided the software interface specification, so if I wanted to write my own software for this, like I've done with so much of my test equipment, that's something that we could do with this fairly easily, and the fact that they're using the standard serial protocol makes that job even easier. Now, the manufacturer claims that the return loss for this device at 3 gigahertz is 17 dB, and we can see on my software that marker A is set to 3 gigahertz. And it looks like we're measuring a return loss of about 17.3 dB. And you can see I've set marker B at the worst case return loss, and that's at 5.13 gigahertz. And it looks like we're measuring 8.17 dB. So because channel 1 is a little special in that it is the trigger input, I wouldn't be surprised if this port behaves a little differently than the other 3. So let's go ahead and check channel 2. So that brings up another point I'd like to make. I had asked the manufacturer if they had any concerns as far as torquing these connectors. Of course, we're working at 6 gigahertz, so it's going to be important to get all that set right. And according to the manufacturer, with this metal case and having such tight tolerances, torquing these connectors is not an issue. Anyway, so again, make sure the torque wrench is perpendicular to the connector like so. And we just pull it over till it clicks and we're good to go. And we can see the return loss for channel 2 is slightly better at 3 gigahertz. Looks like we're measuring about 18.5 dB, so maybe another dB improvement. Next, what I'd like to do is measure the DC resistance of the 4 channels. Here I just have one of my calibration standards out. This is just going to a SMA to BNC adapter, and then I have a BNC to banana adapter. It's going back to a set of 4-wire Kelvin leads, which are attached to my HP34401A. Currently you can see that's reading 0.01 ohms. What I could do is null this out. There you go. Now I'll just go ahead and attach this to channel 1 of the oscilloscope. Again, we're looking for the DC resistance. You can see it's measuring 48.538 ohms. Next, what I'd like to do is just go ahead and power this up and see if this makes any difference at all in the reading. Oh, it does. So now we're at 48.908. Let's just move our connection over to channel 2. I wonder if channel 1 changes because it's the trigger input. Okay, we'll check channel 3. And finally we'll check channel 4. And I think they specified the return loss for these of a minus 17 dB. Alright, and finally what I want to do is just go back to channel 1 and let's see if anything has drifted. And you can see it measures 48.539 ohms. Again, this is channel 1 unpowered, and we started off at 48.538. So this is looking at the data we just collected. Again, channels 1 through 4. This is unpowered and powered, and again we're looking at the DC resistance. So 48.538, 48.339, 48.241, and 47.877. And of course I'm working my way this way through, and then I went back and I remeasured this because you can see there's a definite downward trend. I wanted to make sure that our measurement hadn't actually moved, and it hasn't. So For whatever reason, as we measure the channels 2, 3, and 4, the resistance has gone down slightly for each one. Along the edge, you can see they have some kind of a conductive strip. You can see this is serial number 9. Looks like this is hardware revision B10. They're using a Xilinx Spartan 7 FPGA. A couple of weeks have passed since I've started working on the review for this GigaWave 6400. So let me explain what happened. This is the certification of calibration that was supplied with the scope. I was interested in looking at the bandwidth, and you can see we have rise time here, 20-80%. The typical number is 40 picoseconds. The worst case is going to be 50 picoseconds. And this particular scope measured 37 picoseconds. I had planned on measuring the rise time using this S52 pulse head. This was made by Tektronix. This is using a tunnel diode. We can see this can generate a rise time of less than 25 picoseconds. This was part of a TDR option for one of their oscilloscopes, and I just use it strictly as a pulser. So this connector attaches to a power supply that I made for the device. So when I hooked this up to the scope, I did make the measurement, but what I saw was there was some glitches in the data. So then I started running several tests looking for these glitches and trying to understand what the cause was. So I've been in contact with the manufacturer. I'm going to supply a link to the EEVBLOG thread where we've been talking about this product. So if you're interested in seeing some of the history behind that, you can look it up there. But anyway, so the manufacturer found the root cause recently, and they've asked me to do an update of the firmware of this. Again, this was just held together with these 6 torque screws, and they did supply a wrench with it. I have not taken the circuit board out of this lower case assembly. The manufacturer, I guess, had some concerns about doing that. I understand there's a couple of thermal conductive pads that attach this to the lower half of the clamshell, so I have no plans on taking the circuit board out. But in order to update the firmware on this, you'll notice they have a 10-pin tag connector. So they have provided me with a procedure to update the firmware on this. Use 2 different tools to do that. One will be the Xilinx tools, and of course the other is the ST Micro tools. While I was hunting down my Xilinx tools, I came across these. This is kind of interesting, blast from the past. This is the Parallel Cable 2 model DLC5. So this connected up to your printer port. This is the DLC4, and this is a serial type programmer. These are quite old. Of course, they're not going to be supported by the latest tools. Their documentation talks about this programmer. So this is the platform cable USB. They said that they support both the 1 as well as the 2. The 2 is going to be red. I have used this with Vivado. It does seem to work, but they are quite slow. What we're going to be using to program this is a different one. This one's made by Digilent. It's a model JTAG HS2. Nice thing about this is, first of all, I think I paid like $50 for these a few years ago. The other thing about them is they're quite fast, at least compared to that USB one. They do offer faster programmers if you're needing them to do debug work. So I had all the tools except for this tag connector. This is the part that they shipped me. It's a TC2050 IDC NL. This comes with a small test board. Of course, the advantage to using a connectorless system like this is, first of all, we don't have all these stubs hanging out here. It also reduces the overall system cost. I believe that this cable assembly cost about $40. I can imagine they don't sell a lot of them, but these are quite well made. These pins are all pogo types. I don't know if the camera's going to focus on this, but there's our pins, and you'll notice as I push this down, you can see how the pogo pins retract. This is an ST-Link V2. I bought this when I started working with the low-cost VNAs, so this is what I've been using to reprogram those. And this is my Digilent HS2. So the way this works, I've just got the tag connector. This goes off to this little header pin, and from there we fan out to our 2 adapters like so. So we'll go ahead and upgrade the firmware for this, and we can see if this improves our little glitch problem. So in the back we have our S52 pulse generator attached to the GigaWave 6400. This is our trigger output. You can see this is attached to channel 1, and then our fast rise pulse is attached to channel 2. I'll go ahead and we'll start up their software. We'll start by selecting the GigaWave 6400, and this is what the software looks like. Let's go ahead and we'll turn off channel 3 and channel 4. And let's change our resolution from 32 points per division to 4 points per division. Let's change our time base to, let's say, 10 nanoseconds per division. And we'll increase the position to 85 nanoseconds. Again, if you look at the front of this, it says the pre-trigger precedes the test pulse by 85 nanoseconds. Of course, that's going to be dependent on the cables that we've got attached. So you can see it's asking us to increase the trigger hold off. We'll just change this from 50 nanoseconds to 1 microsecond. And now let's change our scale to 50 millivolts per division and 50. And now let's increase the trigger level from 0. We'll just put in, let's say, 100 millivolts. And it looks like we're seeing the high pulse right there. Oh, and there it's low. Alright, there's our edge. So now let's zoom into this a little bit. So we're going to go from 10 nanoseconds per division. Let's take this down to 1. You can see I can right click on the mouse and I can drag the waveform closer to the center. Let's just zoom into this a little further. We'll take it down to 200 picoseconds per division. And it's looking pretty good. We can go ahead now and turn off channel number 1. Of course, it's still triggering off of 1, we're just not showing it. And let's change our time base down to 50 picoseconds per division. It looks pretty good. So now let's go ahead and we'll try to measure the rise time. So we're going to select channel 2, rise time 2080, and we'll do add. You can see we're measuring roughly 35.2 picoseconds. And 35.6 picoseconds. Parentheses 2, I had asked him about this, and this actually means plus or minus 2 picoseconds. So 37 plus or minus 2. So it could be as low as 35 picoseconds and as high as 39, and that gives us an equivalent bandwidth of 9.5 plus or minus 0.5 gigahertz. Let's try zooming in on this a little further. We'll take it down to 20 picoseconds per division. And you can see we get roughly the same value at 35.65. So I'm going to say it's very close to what the manufacturer had measured. I don't really see any big discrepancy between the two. So while they do advertise this as a 6 gigahertz scope, I think it's pretty conservative. With this particular scope, we're measuring closer to 35 picoseconds, so 0.35 divided by 35 picoseconds is 10 gigahertz. So we're on the upper end of this. It's very possible that the interconnection that they use versus what I'm using here, that could play into it. It wouldn't take much to throw off this measurement. Now this SMA adapter, it's not an airline, but it is a higher quality part than what would say be included with one of the low-cost nano VNAs. Ideally, what I would use with this is a 0.35 adapter. One of the problems with using an oscilloscope like this is it places a lot of constraints on the waveform that you want to measure. One problem is that the waveform has to be repetitive, so this cannot be used to look at something that's non-repetitive, say a glitch for example. It has to be a waveform that repeats. Another problem with the particular technology that they're using, this is a sequential sampling oscilloscope. So the way that this works is we have a trigger. It's always on channel 1. You can't trigger on any of the other 3 channels. A trigger pulse comes in. Again, that can be a rising or a falling edge. We'll call that T0. And then we have some kind of a dead time. And for this particular scope, that dead time is 11 nanoseconds. After that, this is when we actually start the data collection. So on a typical scope, if I say I want to trigger on the rise time of this pulse, that's going to place this right at the center of the screen. With this scope, we won't ever see it. So there's a few ways that we could work around this. Say we have a sample, again it's repetitive, and I want to look at the rising edge. What I may do is set a trigger to trigger on this falling edge, for example, and then sometime later, here's our 11 nanoseconds, say at this time, and then we start collecting the data and we can actually see the rise time. The problem with this technique is, let's say it's not a 50% waveform or it's a very low frequency. The actual edge that we may be interested in could be way out here, say, a millisecond later or something. And the further that we move away from this trigger point, we're going to induce errors. So what we'd like to do is make this thing work more like a conventional oscilloscope. And there is a simple way that we could do that. If we take our signal that we want to measure and we feed that into a resistive splitter, I'll just draw that as 3 resistors, and we'll add this delay line to one output of the splitter. The other one will feed straight to channel 1. We'll set this delay for 11 nanoseconds and we'll feed that to channel 2. So this will be the signal that we want to measure. So what ends up happening now is channel 1 will get the signal coming in, so we want to look at the rise, and then 11 nanoseconds later the same signal is going to arrive on channel 2, and this will show up right at the point where the scope starts to do its data collection. And of course this delay line is nothing more than a length of coax. Again, this particular oscilloscope, they have an equivalent bandwidth based on 0.35 divided by the rise time is 9.5 gigahertz. Again, it's only spec'd for 6 gigahertz. They have a minimum of 7 gigahertz, but you can see they do advertise it as a 6 gigahertz device. So they do make resistive splitters that'll work well in excess of 10 gigahertz. The delay line is really nothing more than a spooled up length of coax, and the length of this coax sets the delay. The problem with using a system like this is that coax is going to make one heck of a filter. So if you take a waveform and we feed this thing in, and let's say that's 25 picoseconds rise time, and we feed this into this length of coax, this is going to look something like this. It's going to come up, it'll get to about 50% of the height, and then it's just going to slowly increase. And this time is going to be well into the nanoseconds for a delay line like what we need here. So it's going to corrupt what this signal looks like. So some of the manufacturers like LaCroix, they'll have a way to model this delay line. Basically you'll give it a coax type and a length, and you can also add in the loss of the splitter. That works to some degree. There's a better way that we can do this. If you follow the channel at all, you know I've done a lot of work with VNAs and these low cost ones. We could actually measure the delay, including the splitter, on a VNA and then measure the S parameters for it. Unfortunately, with this oscilloscope, again, we've said that the return loss of this is like 17-18 dB. It's not very good. So what we end up having to do to make this measurement is we're going to take our trigger input, our channel 1, and we have to attach that to the oscilloscope while the other two are connected to the VNA. So port 1 of the VNA is going to attach to our input port 2, is going to attach to where channel 2 would attach at the output of the delay line. We could also characterize the trigger output, and we do that by attaching port 2 to the non-delayed output, and we'd attach the delayed output to channel 2 of the oscilloscope. So I've gone ahead and I've made a delay line. This is what mine looks like. Here we have our N connector. This is our signal input. And I have two SMA connectors, one for our output. Again, this is the delayed output, and then this is our trigger output. On mine, I've got an adjustable delay line included inside of this, and that allows me to trim for any mismatches of our two cables here. Of course, we can use the software to trim out that error, but in this case, we can just do it with the hardware. Next, we'll be characterizing our delay line. So again, this is our input signal going off to port 1 of the VNA. This would be our trigger out with the yellow. Again, we're attaching that back to the trigger input of our oscilloscope, and then this is powered up. And then this is our signal out going back to port 2 of the VNA. And then we'll be measuring both S11 as well as S21. What we'd like to do is remove the errors from this connector all the way back to the oscilloscope. So including all these cables as well as the delay line. So once we get this set up, these cables have to be used with this system. Now again, this current configuration, we're measuring the signal out. But what we can do is flip the yellow and our orange piece of coax here. So basically flip these two, and then we can characterize our trigger port. And what we can do is store touchstone files for both of these configurations, and we'll be able to import that into their software. So hopefully by de-embedding this, we can actually improve the measurements when using this delay line. Now that we've characterized our delay line along with our cables, what we can do is run a little experiment. So I've got my light VNA 64 out. We're going to be using this as a simple square wave generator. What we can do is select CW frequency. And again, the light VNA has two synthesizers. There's one for frequencies below 150 megahertz, and then there's another for any frequencies above 150 megahertz. If we use the higher frequency synthesizer, it provides a faster edge. So we'll select 200 megahertz. So the output now on port 1 should be a 200 megahertz square wave. We'll go ahead and attach that to channel 1 directly. And we can go ahead and start our oscilloscope software. And we can turn off the channel 4, 3, and 2. And let's just select 100 millivolts per division. We'll take it down a little bit farther. Let's try it at 50. So this is our rise time. So let's go ahead and measure that. We'll select measurement. We'll leave it at channel 1. And we'll do rise time and add. And you can see it's reading, it looks like 154, maybe 155 picoseconds. We'll disconnect our light VNA from channel 1, and we're going to attach that to the input of our delay line. And now we can take our trigger out, and we'll attach that to channel 1, and then we can take our output and we'll attach that to channel 2 of the oscilloscope. And the first thing you'll notice is our rise time now is measuring 202 roughly picoseconds. So it's increased almost 50 picoseconds. And the reason for that again is because we've added this additional length of coax. Let's go ahead and enable channel 2. And let's back up our time. And right here is our rising edge. We'll change our vertical scale to 50 millivolts per division. And you can see the rising edge of this compared to the falling edge of channel 1. You can see that it's much slower. And again, that's because it's a lot longer section of coax. But you'll also notice that the trigger now, again we're triggering on the rising edge, that rising edge is very close to the start of the data collection. But this doesn't look anything like what the waveform should look like. First of all, it's attenuated, and then it's greatly filtered. So the question is can we use that data that we've collected off of our VNA to improve what this looks like? So what we do is we'll select the de-embed function, and we're going to do import S parameter from VNA, we'll select import, and I have this file that I've created with the Agilent PNA called GigaWave signal. Let's go ahead and add channel 2 and rise time. It's much better. It's reading roughly 163, so a big improvement. Let's again just go ahead and turn that back off. Again, we select de-embed, and we'll select no de-embedding. Again, you can see the attenuation because we're not accounting for the 6 dB attenuator, or the splitter essentially. And again, here it is being de-embedded. And you can see again we're measuring roughly 161 picoseconds. We can also de-embed our trigger input. We do that the same way. We'll select de-embed, import S parameters, and for this we use the GigaWave trigger. Let's just flip the edges around. We'll do falling. And you can see it's roughly 157 picoseconds, 158. Again, pretty close to our 155 picoseconds. Obviously, it's a little easier to compensate for a shorter piece of coax. So a few weeks have gone by since I looked at this delay line, and I want to show you some changes that have been made to the software that will help improve this. And again, you can see this one is adjustable. You just have a signal input here. Then we have a signal output and a trigger output, and again the idea is that we're creating a pre-trigger which allows us to actually use the second channel of the oscilloscope to look at the trigger point. Again, this oscilloscope starts collecting data about 11 nanoseconds after the trigger arrives, so if you're actually interested in looking at the trigger point, you would have to use some kind of a pre-trigger device like this delay line. So again, inside of this delay line there's nothing more than a DC splitter and then a spooled up section of coax, and then I have a phase trimmer, which is again kind of like a whole bunch of trombones that are placed in series, and then we can shorten and lengthen this section of coax by moving these fingers in and out. That essentially changes the phase relationship of the signal out to the trigger. The particular splitter I chose is a mini circuits part. It's a ZFR SC-183-S Plus. It's rated for DC to 18 gigahertz, and it is a resistive splitter. Currently you can see I have our light VNA. Its output cable is attached to the input of our delay line, and I've set this for a CW frequency of 100 megahertz. Arbitrarily, it doesn't really matter. I just want to get a square wave out of this. This is looking at the datasheet for the mini circuit splitter. I don't remember what I paid for this, but somewhere probably around $100 maybe, $150. Again, for a resistive splitter, it's basically going to cut the signal in half or give you a loss of 6 dB. You can see that it's not flat across the entire frequency range, which is why we have to characterize the delay line as well as all the cables. This is looking at their latest software. This is preview 2.5.9. It says a few new features that I like. So the first one is when you set up the menus the way that you want them, and that includes all the offset voltages, the scaling, the horizontal settings, any feature that you set, I think. Now, when you hit File and you hit Save Settings, you'll notice that it defaults to default JSON. The way the software now works is if this file is present in this directory, when the software loads up, it automatically loads these defaults. You can still save all your settings into different files and you can load them up as you want, but it just gives you an easy way to basically auto set up the scope the way that you would like it. Of course, there's a lot of other nice features with this software, but one of the big ones, for me anyway, is that we now have this power user. So you go to Options, and you see Power User Mode I'll go ahead and select that. You'll notice now that we have a start, an end, and a step. We also now have the ability to lock the start of acquisition to the left, the center, or the right. Let's just keep this locked to the left. And now what I'm going to do is change our start time to 7 nanoseconds. And you can see it actually starts logging data. I think it's pretty close to about 7.7 nanoseconds out. Again, we're triggering right now on the rising edge of this square wave coming out of our light VNA, and that's on channel 1, which is our yellow trace. And you can see that it's got kind of this little rising edge here. This is one reason that the manufacturer didn't allow you to actually collect data prior to 11 nanoseconds. But if you're using a delay line like what I'm showing here, what that does is it allows us to push that start of acquisition all the way back to around 8 nanoseconds. Essentially what that's doing is it's allowing us to remove cable from inside of the box, and of course less cable, less errors. So if I hook this back up to our VNA and we measure a new set of S parameters for this, this is actually going to be more accurate than what I had originally with the longer coax. What I'm going to do is just enable the min-max. Again, we do that by selecting our little control signal, and we set min-max. Let's go ahead and change this from 20 to, let's say, 10 nanoseconds out. It might be a little too far. Let's try it at 11. I'd like to see some of the other features. And now let's go ahead and adjust our delay line. See how we're moving that closer to the 8 nanosecond start of acquisition. You can actually adjust this thing a little bit earlier if I want to. Again, the idea of this phase trimmer is it just allows me to make this adjustment in hardware versus doing it in software. You can see I'll bring it back the other way. This phase trimmer allows about a nanosecond of adjustment. Again, looking at this kind of rising feature in the channel 1 data, they've actually talked about compensating for that, but unfortunately they're not sure, I guess, unit to unit how much that varies. It sounds like they're also not sure how temperature affects it, but for me that's not really a big deal, because when you're using this kind of a feature, I wouldn't normally be looking at channel 1 anyway. So I have the light VNA set for 200 megahertz CW, and port 1 is connected to channel 1 of the oscilloscope. Alright, so what I've done is I've changed our start time to 14 nanoseconds and the end time to 17 nanoseconds. Again, as I move the start of acquisition closer to 8 nanoseconds, we'll start to see that slow DC slope. And again, that slope only occurs on channel 1. So what we're going to do now is save this. So we'll do export, channel 1, and we'll just overwrite our light VNA 200 megahertz. Now let's connect the light VNA port 1 to the input of our delay line, and again we'll attach the trigger back to channel 1 of the oscilloscope. Like before, you can see this is attenuated quite a bit. What we can do is do file, and we'll do import, and let's reload the file that we just collected, and you can see our rise time is roughly the same. Again, when we're looking at the trigger signal with this delay line, that's a much shorter path, so it affects the rise time a lot less. So let's go ahead and we'll enable channel 2, and now let's change our start time back to 8 nanoseconds, and we'll change the end time to 12 nanoseconds. Now what we can do is add this time shift to our stored waveform. So you can see now as I place channel 2 on the same scale, first of all, the amplitude again, it's cut in half. Again, that's because of our resistive splitter. Let's go ahead and we'll correct for our delay line. Again, we'll select the tool menu, de-embed, specify S parameter, import. And this is our new 8 picosecond delay line. So we can go ahead and time shift our reference signal, get it a little closer. It looks like we have a little bit of a DC offset difference. So let's add, I don't know which way we go with that, maybe 5 millivolts, pretty close. Let's try it at 6 millivolts. It's pretty close right there. So you can see, using that de-embedding function, we can actually do a fairly good job reproducing our signal even after feeding it through this delay line. I like how the newer software drives. This is a lot easier to set up a test like this than it was before, so I thought it'd be good to repeat this test real quick. Next, I'd like to run the GigaWave 6400 over temperature. So you can see in the background here, I've got my environmental chamber, I guess we can call it that. This is nothing more than a packing box for meat. You can see I have a heatsink on top. If you watch my videos, you've probably seen this before. There's a couple of stacked Peltier junctions mounted up inside of here. Does a fairly decent job at cooling. You can see there's added insulation. This cable runs off to our Marconi RF generator. That's tied to the GPS receiver. We'll be using that as our reference. Okay, so here's our setup. You can see the scope down inside. Again, we just have channel 1 connected off to our RF generator, and then I have our 8-foot USB extension cable going back to the PC. Off to my right here you can see a cooling fan, and then there's a shroud that's sitting over the heatsink to help direct that airflow across it. Scope puts out a fair amount of power, so I won't be able to drop this thing into the negative temperatures. I'll try to get it as cold as possible, and then maybe we can get an idea how this drifts. We'll be testing with a 1 gigahertz 0 dBm source. Right, this is looking at their software. You'll notice this is version 2.5.7. Early on I had tried to run a temperature test with this scope, and there were a few problems. One, the software was lacking a min-max function, so I really couldn't see how much the scope was drifting. The other problem was the scope would periodically put out these glitches. I believe that the problem that I was seeing with the glitches was a soldering issue with the scope. Again, this oscilloscope was one of the initial prototypes that was hand soldered, so I've since reworked the entire circuit board, and since doing that I haven't seen any kind of a problem with it. Let's just go ahead and set the offset voltage to 0, and we'll increase the resolution to 100 volts per division. Let's try it at 50. It looks pretty good. And now let's enable the min-max. Let's go ahead and we'll add the frequency for channel 1, and you can see it's reading roughly 1 gigahertz. You can do the rise time, and we can add the fall time as well. We'll go ahead and scale this out to 200 picoseconds per division. And we can drag our waveform off to the start. One of the things I don't like about this software is I can never really see the start of the acquisition. Again, the scope takes a while before it starts actually collecting the data. Currently that's 11 nanoseconds. I would like this to always be off to the left hand side of the screen, but you can see as I change this position, this is the center of the screen, so I could set this to 11 nanoseconds, but it'll show that start of collection right here in the center of the screen. And then as I change the base frequency, of course I lose sight of where that start of collection actually is, so it drives a little funny to what I would expect, but for the purpose of collecting this data, this will be fine. Let's go ahead and we'll add the vertical RMS voltage as well. So in the background here, this is our temperature. You can see we are currently down to about 15 degrees Celsius. This temperature chamber has a platinum thermistor, which is attached to my HP 34401A multimeter. Of course, I'm using my power supply to actually set the current to the Peltiers. I also have a switch box that allows me to change the polarity of the voltage across the peltiers, essentially allowing me to do both the heat and the cool with this box. Again, I'm not expecting this is going to reach 0 degrees. I'll just let it pump down as low as I can. You can see we're down to about 14.6 degrees C right now. What I've done is I've gone ahead and I've turned on the other 3 channels. Essentially what I'm looking at is what's the offset look like over temp. So I've gone ahead and set the min-max for each of those other 3 channels as well. See them up in the center of the screen here. You can see this gets a little busy the way that the software works. The scope has been below 10 degrees Celsius for a little over a half an hour now. Again, this chamber is basically running full tilt. It can't get any colder than this, and it's down to essentially what my room temperature is. If we look at the manual, you can see that they specify an operating temperature of minus 20 degrees Celsius to 50 degrees Celsius. Unfortunately, I can't run it down that low for this testing. So as we look at our min-max for all of our waveforms, you can see it really hasn't changed a lot. Again, channels 2, 3, and 4 are set for 10 millivolts per division, and I do have the min-max enabled for each one of those. Looks like there might be a slight shift in the phase for channel 1. Oops. It's one of the problems with this software. If you touch anything with the mouse, so if I zoom in or zoom out, we just lost all of our min-max data. But keeping in mind it really hasn't changed a whole lot. So keep that in mind if you're using the min-max. I think what I'm going to do is go ahead and we'll change this over to heat. So we'll change our set point to 50 degrees Celsius. Obviously it'll be a lot easier to heat up the oscilloscope. We'll have no trouble hitting the 50 degrees Celsius. It's taken about a half an hour to ramp the temperature back up to 50 degrees. You can see there's about a 3 degrees C overshoot. Now it's starting to settle in on 50. What we'll do is just let it sit like this for maybe another hour or so. Give our oscilloscope plenty of time to settle in. Being careful not to move the mouse on the screen here. You can see it's definitely caused some kind of a phase shift. It's possible that the oscilloscope's trigger input is sensitive to temperature. Our oscilloscope's been at 50 degrees Celsius for roughly 45 minutes now. And you can see it continues to shift a little bit. Looks like the input offset voltage has not moved for channels 2 through 4. But you can see the phase has definitely continued to shift for channel 1. Again, it might just be the trigger circuit. It doesn't look like the amplitude is changing a whole lot. Maybe slightly if you kind of look right here at the red. Looks a little bit higher than over here where the peak is now. Overall, it appears that it's fairly stable with temperature. Alright, I'll let this thing cool back down. We can go ahead and take it back out of the box. Again, this is the certificate of calibration that was applied with this particular oscilloscope. What I'd like to do next is look at the THD. Here we can see 1 gigahertz sine wave. Typically it measures minus 40 dB. The worst case is minus 30 dB. And this particular one measured 37.65. So here we have our oscilloscope. I've got channel 1 connected up to my RF generator, which is currently set for 1 gigahertz at 10 dB. That should give us fairly close to the full working range of our oscilloscope. So this is looking at the current manual. So down here we can see for 1 gigahertz they're using 50 nanosecond position, 100 nanosecond hold off, and a 1 nanosecond per division with 32 points per division. Let's go ahead and we'll fire up their software. What's interesting about this software, like if I double click the GigaWave, you can see that will not start it. You have to select OK. And here it's running. Let's go ahead and change our offset to 0. And we'll just turn off the other 3 channels for now. So now we can come over to Tools and we'll select FFT. And we'll just wait for this thing to capture. Right there we have it. So looks like we're measuring roughly 34.8 dB. Again, they specified 37.65. So when I was working on editing the video for this scope, I had realized just how far off our 1 gigahertz THD measurement was. Again, we had measured 34.8 dB. The manufacturer had measured 37.65. The maximum is 30 dB, so we were under that with our measurement. But the question is why was that measurement so far off? Again, that Marconi 2024 RF generator that I was using for this test, it is a synthesized RF generator, so the output isn't all that clean. So what I have here is a interdigital filter. Again, this is just connected to channel 1. So let's go ahead and we'll remeasure the THD. So again, this is looking at their software. You can see I'm applying about a plus or minus 500 millivolt signal. Let's go to Tools and FFT. And you can see we're measuring minus 37.43. Let's just change all of our settings back to what the manual suggests. So 50 nanosecond position, 100 nanosecond hold off, 1 nanosecond per division with a 32 points per division. You can see 32 points per division, 1 nanosecond per division, position at 50, and our hold off is set to 100. Let's have a look at our FFT now, see if that improves anything. Looks like it's a wash. It's measuring roughly minus 37.4. There's 37.5. So it's a lot closer to their minus 37.65. Alright, back to the review. So for 100 megahertz, the typical total harmonic distortion is minus 55 dB. Again, they measured this particular unit at a minus 58.4 dB. I've gone ahead and reset our RF generator for 100 megahertz. And looking at the manual for 100 megahertz, they're using a position of 300 nanoseconds, a 500 nanosecond hold off, 10 nanoseconds per division with 32 points per division. So again, we're at 32 points per division, 10 nanoseconds per division with a 300 nanosecond center point and a hold off of 500 nanoseconds. Let's go ahead and we'll bring up the fast Fourier transform. And you can see it's measuring 39 dB. That's 11 dB away from our absolute worst case number that they specify. So what's the problem? Well, I'm using a synthesized RF generator. It's a Marconi 2024. So to make this measurement, we're going to have to clean up that signal a little bit. So this is what we're going to be using. This is a small filter that I built up. Let me just go over that real quick with you. This is just a simple 3-pole bandpass filter with a center frequency of 100 megahertz and a 10 megahertz bandwidth. This is made up of two 3 picofarad capacitors, a 360 picofarad cap, a 6.8 nanohenry, and then two 820 nanohenry chokes. For the two 3 picofarad capacitors, I'm using two 1.5 picofarad NPO capacitors. Those were made by AVX, KGM now, so it's KGM 15A CG1H 1R5. For the 360 picofarad, I'm using two 180 picofarad parts made by American Technical Ceramics. These are an ATC 100C181. And then for the two coils, those are made by Coilcraft. For the 820 nanohenry parts, those are an 0805 CS-821 XJL. And then for the 6.8 nanohenry, it's an 0805 CS-060 XJL. These are our two porcelain ATC components. These are our 4 AVX parts here. And then you can just make out our 3 coil craft inductors. Again, we'll just attach this right between the RF generator and the oscilloscope. And you can see it's knocked the signal down quite a bit. We have to let this thing go ahead and scan through. And let's see what our FFT looks like now. Looks like 56 dB. Let's go ahead and we'll increase the signal level a little bit. Basically make up for our 6 dB loss. Now we're talking. So minus 60.5 dB. Again, going back to our calibration certification, I believe that both of these numbers are accurate. Again, when they took these measurements, they did use a different technique, but we're certainly well within the ballpark. Channel 1 is currently attached to my Marconi RF generator. That's been set to 10 dB at 2 gigahertz. You'll notice that I have the grounding straps on the other 3 channels. Again, looking at their software, we're on 200 millivolts per division right now. You can see it's roughly about plus or minus 800 millivolts. Again, they specify this thing for plus or minus 950. I'm not really trying to stress this oscilloscope by overloading it. So what I'd like to do now is zoom into the other 3 channels. So let's go ahead and turn these on. If I select this icon here, it should zero out the offset. So you'll notice that channel 2, there's a little bit of bleed through here. Let's go ahead and we'll measure this. So we'll go add measurement in channel 2, and we want the vertical, and let's just do AC coupled RMS. It's fine. Add, and it looks like about 2 millivolts of RMS noise. Let's have a look at the other 2 channels. So we'll add 3 vertical RMS again. You can see that's like 120 microvolts, and let's go ahead and add channel 4, and you can see about 106 or so microvolts. So as we physically get closer to channel 1, the isolation isn't near as good. Now, I've brought this up to the manufacturer, and they told me that this is well within the specifications of the oscilloscope, which I'm fine with, but that led to a discussion about them changing the case design to try to improve this isolation. Alright, so this is our new case, just sent to me. I guess this came with a set of thermal pads. It basically looks identical, same markings. From the back, you can see it's identical as well. There is a serial number that was etched into the back. You can see serial number 9, where this new case has not been marked. So I had this apart before. I wasn't able to show you the bottom side of the circuit board because the manufacturer had recommended that I not take that apart when I reflashed it. Unfortunately, again, this unit had some other issues, and I ended up taking it all the way apart to rework the circuit board. Unfortunately, I didn't capture that on camera, and the reason for that is I was doing all this very fine soldering with this, and I did not want to mess up the circuit board. So now that it's apart, I'll let you have a look at it. Quite a bit going on with this scope on the back side. I couldn't tell you how much I've actually reworked on this board, but quite a bit of this. So basically all these LCC parts, I've gone back and resoldered all those. Same thing with the connectors. There were issues with the soldering as well. Now again, this was one of the first prototypes and it was hand built, so this is by no means a reflection of the company's quality once they're in production. All these LCC parts here were resoldered. Here we can see our thermal pads. You can see how they've taken a set. What their concern was about me pulling this out was if I reinstalled the circuit board, that you may not get the same thermal conductivity and the board would end up overheating. Now I've ran it like this for, geez, it's been at least a week, and I have not seen any problems after having this out. But you could imagine taking this apart so many times, it's not going to help it at all. So again, I believe that they've sent me brand new pads with this new case. It doesn't appear that the bottom half of the shell has had any changes to it. It looks like it's all on the top half. You'll notice how they originally had this single pocket with a single RF gasket riding across the length of it. Now we have these individual pockets, each with their own RF gasket. So let's go ahead and we'll reassemble this with a new case, and then we can recheck the isolation between those channels and let's see if it's improved it at all. They did warn me as far as tightening these down that you want to keep them even. We'll just kind of do a little cross pattern on them. For now, we'll just very loosely finger tighten them. Do a little bit of a squeeze with our fingers. There we go. We'll just do our final torque here. Give it another quick check. Looks good. And we'll do these two inside ones. There we go. And it looks like channel 4 may be a little bit lower now. Channel 3 is kind of a wash, but again, these are way down the muck. You'll notice that channel 2 reads about the same. Again, we previously measured 2.02 millivolts, and it's basically 2 millivolts right now. So yeah, it doesn't appear that going to the new case has helped with the isolation at all. Maybe it does at higher frequencies. Again, we're only testing at 2 gigahertz. Again, if you're out on the forums, you can see where I posted data using this oscilloscope all the way up to 11 gigahertz using this extender here. Let's just go ahead and I'll set that up for you real quick. So again, this frequency extender is for the X band, so it allows me to extend the range of the nano VNA all the way up to about 12 gigahertz. If you're interested in seeing what this frequency extender looks like on the inside, you can watch the series that I made on waveguides, and we'll just select link, and we can select sweep. We'll go to setup diagnostics. We can enable the extender. We'll go back to the main page. It's currently set for 8 gigahertz. Let's just go ahead and up this a little bit. We'll go to 10 gig. And let's see if we can pick this up with our oscilloscope. So we'll turn off the other 3 channels. And let's change it to 5 millivolts per division. Right there you have it. See how it's showing us our waveform. So go to 10 millivolts. And let's go ahead and add our frequency for this. So frequency of channel 1. Let's see what it comes up with. So it's saying 10.018, 015 gigahertz. Fairly close, I would say, to 10 gig. As long as we have our frequency converter out, let's just try a few other experiments with our GigaWave 6400. So off to my left, you can see I've got some waveguides. A waveguide is just another type of transmission line. It's nothing more in this case than a hollow tube. This is roughly the same size as what we're using here. This would be a WR90 or rectangular wave. 90 defines the dimensions of the waveguide. This is a homemade slotted line. I use this to measure the frequency as well as VSWR. This particular set of waveguides is set up for a test I was running. So here's the output of the frequency converter, which goes to our input. This input is tied to a magic T. This piece down here is a mechanical iris. This essentially is a very small slit, and then I can control the aperture size with this little thumb screw here. And then this back is a cavity, and then I can change the length of it with this micrometer. This basically, between these two adjustments, allows me to resonate this cavity. It's got a very high Q. This input here is where I can put a test sample. Again, looking at our software for the light VNA, you can see I've set our CW frequency for 0 Hertz. Now, of course, our frequency extender has an internal oscillator, and that's running at 7.86 gigahertz. So let me just show you on our oscilloscope. You can just sort of make out the waveform. It's definitely there. You can see it cannot measure the frequency, and I can't zoom in any farther. Again, this is 5 millivolts per division. Let's just try it in our custom mode, and let's try changing this to 1 millivolt per division. Nope, you can see it will not allow me to go any smaller than 5 millivolts per division. So watch what happens as I change our frequency to 10 gigahertz. You can see how it's actually saturating on the bottom. That's because I've set this CDF range a little too low for this signal. So let's just bump this thing up to, say, 50 millivolts on both the high and the low side. So notice it looks pretty much like a sine wave now, and you can see it's measuring 10.085 or so. So the frequency is fairly close to what we would expect. Again, we can back this start time up now. We can go all the way back to 7.7 nanoseconds. You can see now how our signal has this gradual increase in the DC offset. Again, that's a function of the oscilloscope. That has nothing to do with our frequency converter. Let's just bump this up to 11 gigahertz, and you can see how that's really attenuated the signal. Again, first of all, this oscilloscope was only rated for 6 gigahertz. We're running it at just about double that. The other problem is we're working with some very small signals, but the fact that the scope can even trigger it all and show you a waveform, it's pretty amazing. If we take our oscilloscope and we attach it directly to the output of our frequency extender, now we can see our waveform. You'll notice that it's calculating a frequency of 11.2 gig versus 11 gigahertz. Again, I think that error is due to the signal being so small. So let's have a look at some digital signals. So off to my left, this is a eval board that was produced by Digilant. It's got a small Xilinx FPGA on it. Then I have this homemade breakout board. This board actually has 4 resistive probes on it, so we can attach the coax directly to our oscilloscope. This board is quite old. I doubt that they make this particular one anymore. The FPGA that they use is a fairly low-end part. This is looking at the FPGA design. This is nothing more than a phase lock loop. That clock then drives a pseudo-random sequence generator, and then that pattern is coming out on the 4 channels. Let's go ahead and bring up the oscilloscope. So this is what it looks like. So channel 1 is the data ready signal. Channel 2 is the output clock out of the phase lock loop. Channel 3 is the PLL's input clock. And then channel 4 is the data signal. Let's just zoom out on this a little bit further. What we can do is increase our step size to a nanosecond. Now again, this channel 4 is totally random. Let's go ahead and we can select the other scale mode, and you can see this is how they would normally show the eye diagram. You can change the intensity, maybe get a better view of what that eye diagram looks like. What we can do is move our trigger to look at the data signal. So I'm just going to swap channel 1 with channel 4. So now we're triggering off of the data signal, and again, it's very difficult to tell where the actual eye is. You can see there's maybe a break here, 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 and here. That would be correct because we're clocking that data out on the falling edge of channel 2. Again, the idea, if you're using a scope that's using some kind of sequential or random interleaf sampling, you want the signals that you're interested in looking at to be repetitive. And of course, we're feeding in a pseudo-random sequence, so it's not a surprise that the scope doesn't perform very well with this waveform. I provided SJL with an opportunity to critique my review before I placed it up online. One of the things that they noticed was the poor contrast ratio when we're looking at eye diagrams. So they've provided us a new version of the software which allows us to increase the intensity. It also allows for a color gradient. One thing I want to mention about this setup that's a little unique, you'll notice that this is all set up on my bench instead of on my desk. This is another 8-foot USB 2.0 cable. Both of these cables are going back to a USB 3.0 powered hub, which then attaches to the PC. The overall cable length now from our oscilloscope back to the PC port is probably close to about 15 feet. I've ran several tests with this configuration off camera and I'm not finding any problems with it. We'll start by loading up our FPGA project, and we can go ahead and launch our oscilloscope software. Right, you can see all 4 channels are set for 200 millivolts per division. We currently have a hold off of 100 nanoseconds and a resolution of 8 points per division. Let's go ahead and we'll disable the vector mode on channel 4. Let's zoom into this a little bit. We'll select 50 millivolts per division. Maybe a little large. Let's just try it at 100. Now let's increase the number of points per division. We'll take it to 32. You can see I have the brightness turned all the way up right now. Let's zoom into this a little bit farther and we can capture a single eye. We'll take this down to 2 nanoseconds per division. That's about as zoomed in as we can get. Now let's try increasing the number of data points to 128. Oh yeah, this is a lot better than what we had. You'll also notice that they've got this color gradient now. Let's go ahead and turn that on and let's dial back our brightness. Oh, very nice. Let's turn off some of these other displays. And now let's change our scale to 50 millivolts per division. And it looks pretty nice. So I'm glad that they took the time to watch the review and catch this. From what I understand, based on their comments, one of the main purposes for buying an oscilloscope like this is for signal integrity. So they didn't want me to present what they had, knowing that the contrast could be improved. I'd say they did a pretty good job on this. I think it only took them a day to roll this out. Alright, on with the rest of the review. So currently channel 1 is attached to my ARB. Looking at the software, you can see it's displaying acquisition weight. The way that this scope works is it has an internal trigger circuit. So even if there's no signal present on the input of the scope will automatically trigger. One of the benefits to this is that we can actually look at very low frequency signals right down to DC. We go ahead and I'll turn on our ARB. You can see I'm putting out a ramp right now. It's a very low frequency. Just switch this over to a square wave. Actual frequency is 200 millihertz with this. Here's a triangle. And here's a sine wave. But if your goal is to look at very low frequency signals like this is probably not the device you want to be using. The first DSO I ever purchased was my LaCroix 7200. I've shown that in several videos. That particular scope has a 4 gigahertz bandwidth and it does use wrist mode, which is also a sampling oscilloscope. One of the things that I still use that oscilloscope for is to look at ignition waveforms. Ignition being like automotive ignitions. Scope does a pretty good job with that at 4 gigahertz. I've got some special probes that I've made up. I'd like to demonstrate something similar using the GigaWave 6400. So here I have a spark gap transmitter. I had made a few videos showing different ones that I had put together. This is the last one that I built. This one will operate up to about 28 megahertz. The first reason I want to demonstrate this is, first of all, this oscilloscope uses USB. And from my own experience, USB is notoriously poor for working in environments with high noise. So it's a nice thing about that old LaCroix scope is it doesn't use USB. The other reason I want to run a test like this is ignitions are not fast. Yeah, the signal coming off of them is very fast, but the pulse time, or how fast the engine is cycling the ignition, is very slow. Think about it, if you had an engine that's turning at 600 RPMs, you divide that by 60, it's basically 10 hertz that ignition is firing at. So it's not a fast system. So I thought what I'd do is just fire this transmitter up. You can see it's just got a LED attached for a load here, and I have a small loop antenna attached to our oscilloscope. I'll just hang that next to our coil, and we'll see if we can pick up a signal with this, and maybe we can get an idea how robust the USB interface is with this scope. The other thing is just how fast it's going to update with such a slow signal like this. So again, if I turn on my power supply, we are not talking about a lot of power here. You can see our little LED is just barely lighting up. Let me go ahead and I'll tune the frequency of this, and you can see it doesn't have a whole lot of an effect on the output power. So here we can see that the oscilloscope is indeed triggering. It's also displaying the waveform. It looks like it's going to be about maybe 9-10 megahertz. You can see I have very poor resolution right now. Our step size is set to 10 nanoseconds. We have a end time of 500 nanoseconds. We can increase this 10 maybe to 20. I'll bet you the resolution gets pretty bad. You can see this is going to be very choppy. But notice how slow the update rate is. Let's take this down to 5 nanoseconds. Then we'll drop our end time from 500. We'll just cut it in half to 250. You can see the update rate is still really slow. Again, that's really a function of how fast I'm getting these triggers. What I'm going to do now is double the frequency from 1 kilohertz to 2 kilohertz. Now what I'm going to do is adjust the tuning cap of our transmitter, and let's just see if this affects the communications at all. You can see our screen has stopped updating. Transmitter's probably running close to about 20 megahertz right now, maybe. Let me just go ahead and turn off the transmitter real quick, and let's see if this thing will start to scan again. So it looks like it did at least revert back to the wait state, so I didn't completely knock it out. Again, I've got no antenna or anything off of that coil right now, so this is a pretty lame test compared to what I normally run. But you get the idea anyway of why I don't like seeing USB used on any kind of test equipment. What I'd like to do next is spend some time going over their software interface. The way I'm going to do that is I'm going to show you some software that I wrote, and I'm going to be using LabVIEW. Again, this is some software that I wrote specifically for this GigaWave 6400. One of the powerful things about LabVIEW is I can generate some fairly complex software in a short time. At the top of the menu, you can see I have different buttons that allow me to operate this scope. On the far left, we have the self-test. This is having the oscilloscope perform its own internal self-test. You can see it passes. We can also have the oscilloscope identify itself. Info provides us some background about the scope. I believe this is firmware version 13, and I think that this is the serial number, so serial number 9. We can also perform a calibration. Rising edge sets the rising or the falling edge trigger. I can also record waveforms to disk, and I can use the open feature to play them back. Really, the most complex thing with this program is converting the data off of the oscilloscope and getting that into a voltage. So let me just show you the source code for that. So this is the subroutine. It's taking the input voltage along with the CDF, and that's converting that to our fitted voltage. So this is looking at the source code. These are some of the notes that the manufacturer had written up in the forums. The first thing that they had talked about is discarding all the data where the CDF is outside of the range of 0.1 to 0.9. That's what this function is doing here. So it's basically collecting all the data that is within inside of that boundary. Next thing we need to do is calculate the weights for the least squares fit. And they provided us with this formula here, which is this section of code here. The weights are feeding into our least squares fit, and we perform an interpolation off of that to get our Gaussian fit. They also have some other checks for out of boundary conditions. This is looking at our main routine. There's 3 loops. This top loop is our main processor, the middle loop is our transmitter, and the bottom loop is our receiver. So for example, if we look at how a calibration is performed, you push the calibrate button, it takes this calibrate message, puts it into the message queue. That queue gets sent down to the transmitter where it pulls the command cal, it appends the carriage return to that, and then sends it out the serial port. So not a whole lot to this, but there are some benefits to writing your own software like this, especially at this point. Because their software is so new, it doesn't have a lot of features, so you may have tests that you want to perform that their software just doesn't have those features yet. You could certainly write your own software to implement those. So let's just use this software to run some additional experiments. Again, we're just going to be using our light VNA as a signal source, and you can see port 1 is attached to channel 1 of our oscilloscope. You can see I currently have a resolution of 10 picoseconds, and I'm recording for 1.5 nanoseconds. It's a fairly high resolution graph. This is what our rise time looks like. Somebody up on the forums asked if we were looking at the rise time, how much that would vary. There's a couple of ways that we can look at that using this software. I have a min-max so we could get a visual representation of how much it moves. The other way we can do that is in the lower right, I can select what channel I want to look at, and then I can plot the histogram. So I've just got that set right now for the rise time of channel 1, and that'll show up in the graph in the lower right. So what I'm going to do is just let this run over the course of the day, and let's just see what this histogram looks like. This is giving you an idea what the histogram looks like for the rise time. I'm going to reprogram our light VNA for 4 gigahertz CW. I'm going to change our boundary conditions to plus or minus 500 millivolts. I'm going to set our range to 5 nanoseconds, and we'll keep the resolution set for 10 picoseconds. Again, at 4 gigahertz, the period is 250 picoseconds, so this should provide us plenty of resolution. Again, at 5 nanoseconds with a 10 picosecond resolution, this will take it some time to collect all this data. Alright, you can see we've collected between 11 and 16 nanoseconds, or 5 nanoseconds total. Now that we have this data, you can also plot the THD. You can see we're close to a minus 20 dB. So here we can see the eye diagram. This works a little differently than their software. So essentially what we're doing is we're taking all these cycles and we're stacking them on top of one another. Up here we have our jitter measurements. Again, to really get some useful data off of this, we would want to collect for a lot longer time, but it's certainly possible to use this oscilloscope to make these measurements. You just have to have a lot of patience. Let's go ahead and change our start frequency to 3.5 gig, and then I'm going to set a stop frequency of 3.501 gig. Just going to give it that slight bit of deviation. And now let's go ahead and collect a new sweep. That little bit of deviation should really throw off our jitter measurement. It should also close the eye up quite a bit. Again, keeping in mind, basically now our scope is sampling asynchronous with the waveform coming off of this VNA. So I'm expecting our noise is going to increase a fair amount. Alright, let's turn off our min-max. You can see how much that's affected the noise. Let's go ahead now and look at the phase. You can see that's closed the eye diagram right up. What I'm hoping for long term is that the manufacturer continues to develop their software and they start to implement some of these more complex features. But you could certainly roll your own software. That's one of the things I like about this oscilloscope, is it's very easy to interface with. Well, I think that's going to be it for this review. Hopefully I provided you with enough examples to give you some idea what this scope is capable of and if it would fit your needs. Again, looking at our calibration certificate, the manufacturer had read a 20-80% rise time of 37 picoseconds. I measured closer to 10 gigahertz with this particular scope. At 100 megahertz, they had measured a total harmonic distortion of minus 58.4. I measured something a little bit lower than that. At a gigahertz, we were pretty close to that 37.65 dB. So I have little doubt that they're meeting what they claim. I'd like to talk a little bit about the pros and cons of buying a unit like this. First of all, if you followed the thread on EEVBLOG, you know this company has been very responsive to every bit of feedback that I've provided them. They've addressed issues that I found, they've added features, and they've done that at a very rapid pace. So from a service standpoint, I've been very impressed with their company. As far as the scope itself, it's got a lot going for it. First of all, its size. Again, it fits in your shirt pocket, but it's also very light. The other thing, it's rugged. Again, it's a solid aluminum case. There is no plastic. Again, this particular scope costs $2,495. That's US. I believe the only scopes that are out there that would compete with this are probably Picotech's 9400 series. They do offer a 4-channel 5 gigahertz version. Price-wise for that scope, I think you're looking at over $10,000, but it also has some other advantages too. I've written my own software to communicate with this scope. The software interface spec is pretty straightforward. Another real advantage with this is, of course, it's very quiet. Compared to my LaCroix, I think that's got 6 fans in it, maybe 5 fans. It sounds like a hurricane when it's running. As a matter of fact, all my oscilloscopes are pretty loud when they run. Let's talk a little bit about the cons. The biggest problem that I see with this is that the software is fairly new. It's going to improve, but the way it stands today, it's pretty feature limited. But I'm sure based on the month that I've owned this, it's going to get a lot better. The next big problem with this is it doesn't work like a standard oscilloscope. With this scope, you can't see where the trigger is. Now there are ways to work around that. I've showed you this delay line. Of course, you're going to give up a channel to do that, and you're cutting the signal in half. But maybe that's an option for you. The next problem is how slow the update rate is with this. Again, they're asking for a minimum of 500,000 triggers per second. And as I've shown you with something like an ignition system, those triggers are very slow. They could be sub 100 hertz. That, of course, slows down the sweep rate. But even with very fast triggers, the sweep rate is very slow with this. Now, I've talked to the manufacturer about that. They think that there may be ways to actually speed that up. Not a small amount, but we're talking maybe 10 to 100x fold. We'll just have to wait and see what they come up with. Another thing I don't like about this, there's no on-off switch. So if you want to turn this off, you have to pull the cable. Of course, that's wear and tear on the cable. And if you leave it plugged in, it's just sucking power off your PC. If you're running this off of a laptop, it's certainly something to consider because this draws a fair amount of current. That's why they're using the USB 3.0 port. Well, I think that's going to be it. I hope you enjoyed the review. Well, for now, we'll see you in the next video. Later.